There are two important number theoretic notions. One we've discussed, it's called the greatest common factor, and the other is the least common multiple. The greatest common factor is useful in describing what it means for two integers to be relatively prime. The greatest common factor of P and Q is a number R such that R divides P and R divides Q. These two things taken together, if you take an integer which divides P, then divides Q, these statements, that means that R is a common factor. Take any integer which divides two others, then it's a common factor of both. Right? R divides P and Q, and if S is another common factor, i.e. S divides P and S divides Q, then S divides R.
You have is instead of S on that one.
And is, let's assume, and S, I'm sorry, yes, and S. So let me read this. R divides P and R divides Q. That means that R is a common factor. So if the greatest common factor of P and Q is R, means that R is a common factor, and if S is any common factor, S divides P, i.e. S divides P, I should put this in parentheses, and S divides Q, then S divides R. Right? That's what makes R the greatest. So for example, if we look at 30 and 18, a number which divides 30 and divides 18, one choice is 2. 2 is a common factor. Another choice which divides 30 and 18 is 3. So 3 is also a common factor. Another number which divides 2 and 30 and 18 is 6. 6 is also a common factor. Are there any other common factors? Well, 1 is always a potential common factor. I should have listed it first. 1 is a common factor of both, of course. That's essentially always true. 2 is a common factor in this case. 3 is a common factor also. So is 6. Any others? No. Since there are no others, 6 is the greatest common factor. So the greatest common factor of 30 and 18 is 6. And every other common factor, including 6, divides 6. Right? So 3 divides 6, 2 divides 6, and also 1 divides 6. So the greatest common factor has the property that is a common factor in every other common factor. Okay? Two integers are relatively prime if their greatest common factor is 1. So, given two integers, and if you want to go about the process of finding the greatest common factor, one standard technique would be, if I work with 30 and 18, 30 has a unique representation as a product of primes. I can write 30 is 2 times 15, or 2 times 3 times 5, And I can write 18 as 3 times 6, or 2 times 3 times, actually, let me write it this way. 2 times 2 times 3. 2 times 3 times 3, right? 3, yeah. 2 times 3 times 3. And then make the observation, given these two values, that I want to include every prime, including as many times as it occurs in both, in order to generate the greatest common factor. So notice they have 2 in common, they have 3 in common. This actually has 2 3s, but this has only 1 3. So one way to generate the greatest common factor is to split it up as a product of primes and see what this is. So the next exercise in here is to find the greatest common factor. Well, part of it is to find the greatest common factor, like a 42 and 56. You can proceed like I just did there. The greatest common factor is also related to something called the least common multiple. The least common multiple of 30 and 18 is an integer that both 30 and 18 divide. Okay? And it is smaller than all other integers that both 30 and 18 divide. That's what makes it the least. So given a prime factorization like this, you can see how many primes they have in common. That determines what the greatest common factor is. To see what the least common multiple is, notice every prime that appears on either of these two lists must be part of the least common multiple. 2 is here. 2 appears to the power 1 in this case, so it must be there in the least common multiple. There are 2 copies of 3 here. Both of those must be there in the least common multiple. 5 is also there because of this. So the least common multiple we can generate by making sure that every prime that appears on either of these two lists is here, and the power to which it appears down here is the highest power to which it appears on either of these two lists. So 2 is raised to the first power because it's 2 to the first in both of these. 3 is raised to the second power because this I can write as 2 times 3 squared, and therefore 3 squared must be there. And 5 is raised to the first power in both of the, in only that one case. This is the least common multiple in terms of the prime factorization. So the least common multiple of 30 and 18 is, this is 9 times 10, it looks like 9. Any integer that 30 and 18 divide is called a common multiple. The least common multiple is the smallest, and that is true in this case. So then, notice if I take 30 times 18. Here is a choice. Here is a choice for a common multiple of 30 and 18. Multiply the two together. If, for example, you're adding two fractions, one choice of the denominator is always the product of the two values in the denominator. That will work, right? But it isn't necessarily the smallest choice of an integer that's going to work, right? Notice I can take 30, or any number here, and write it as, say, K1 times the greatest common factor of 30 and 18. The greatest common factor of 30 and 18 divides 30 and leaves something else left over. Right? In this case, oh wait, this is K1. The greatest common factor of these two is 6, so I can write this as 5 times 6 for 30. And for 18, I can write it as 3 times 6, the greatest common factor. of 30, or 30 and 18, which is 6. 30 and 18, again, which is 6. Right? So if I take the product of these two, right, the product of these two can be written as 5 times the greatest common factor, that's 5 times 6, which is 30. And 18 is 3 times the greatest common factor, 3 times 6, which is 30. The least common multiple doesn't need both of these, in the sense that 5 times the greatest common factor represents 30. 3 times the greatest common factor represents 18. This is overkill in terms of, in terms of finding a number which both 30 and 18 divide. You see that? The greatest common factor only needs to appear once. But the greatest common factor is in both of them, so I can cancel it out in finding a smaller number such that both of them divide. Notice the greatest common factor, notice just because I have one copy here, and I have 5 times 6, which is 30, and so 30 divides this, and I have 3 times 6, which is 18, so 18 divides the right-hand side. Right? And therefore, when we put this together, we get 5 times 3 times the greatest common factor of 30 and 18. What is that? That's the least common multiple of 30 and 18. All of those factors must be there, but nothing else. So I can compute the least common multiple of m and n, any two integers m and n, looks like their product divided by the greatest common factor of m and n, because that gets represented twice. So you can write the equation this way. Compute the greatest common factor. You can always get the least common multiple by dividing the greatest common factor into their product. Okay? Or if you know the least common multiple, you can get, notice rewriting this equation, I can write this in a couple of different ways. The least common multiple of m and n times the greatest common factor of m and n looks like the product of m and n. Or, same equation, the greatest common factor of m and n looks like m times n over the least common multiple of m and n. This is all the same equation, just solving for either the least common multiple, greatest common factor. I'm sorry, I did this. There are really only two on this list. You can write the LCM this way or the GCF this way. The other one that I meant to write, it's here. You can write the product this way. Yeah. So this one, least common multiple looks like this. Greatest common factor looks like that. And this is what the product of those two looks like m times n. All of those are exactly the same equation. Exactly the same equation. So you're probably asking yourself, how do you go about finding the greatest common factor? You can see that it's very useful in figuring out what the least common multiple is. And one way to do it is to do this, but that requires you to find a prime factorization, which can be tricky business, right? Which can be a tricky business. As a matter of fact, some of the security codes are based on finding a prime factorization of the enormous integer, finding the primes which divide it. Maybe the integer has 200 or 300 digits, right? And so you could break the code if you could factor it into primes, but even a computer might take years in order to try to figure out what the correct primes are. So this is a practical way for finding the greatest common factor when you can see right away what those factors are. But in general, for very large integers, you really want an algorithm for finding primes. Finding the greatest common factor.